Right. So if you have a wrench, okay, as you've seen here, so we can actually analyze using a two-dimensional. I mean, in this case, uh, you have a stainless steel. It's made of stainless steel with a thickness of 3 mm. So we want to determine the maximum deformation and the distribution of the stressor, equivalent stress or Overmeister stresses under the given distributed load and the boundary conditions. So here, you have a load applied at here. So basically this is fixed, right? You have fixed boundary condition at here. Basically you want to open up the basically a nuts, something like that you're applying a force pressure at this particular site itself, okay, to turn and yeah to unscrew it, right? So we want to determine what stress and the deformations of this particular wrench itself, okay, when it is subjected to a pressures of, here is referring to 2 megapascal, then fixed at here itself, what will be the deformation of this wrench and also the stress induced, okay? So it can be, of course, if you can draw in 3D, then yes, but then in this particular case, a two-dimensional is sufficient enough. All right. So using design modeler to model it, right? A so-called surface bodies with of course with a thickness, right? Then here, of course, remember to put in two dimensionals. Okay, surface body must be checked. Two dimensional have to be changed. So to find the two dimensionals types of elements. So this is the step by step guides for creating the model using space claim. Right. So you can also try it. Then here, basically under mechanical, once you have done it, so you can turn on the mechanicals. So here, that day we are choosing under the what we call the 2D behavior. That day, I mean the previous the fountain example, we are using axis symmetrics, right? So here we are using a plane stress, right? So you basically this default is also plane stress. Okay, so we are using plane stress assuming non-zero strain in the z directions, right? So of course you can change to other types of behavior, like plane strains that we have mentioned. Only strain is zero, so the z-axis stress it have to be considered. So that is how you choose it. Okay, you have to change it later on. So it's a static structure again. So you choose a static structure. So I have tried both, okay, using space claim as well as design modelers. So in terms of the modeling parts, I will leave it to you. Basically, I think the guides are sufficient enough for you to, is clear enough for you to model it up. Okay, so before you start, remember to, let's say now I have this. So this is stainless steel, so you have to create a new material. So under here, you have to create a new materials, okay? Like what we have done previously, let's say stainless steel. Then you have to put in your isotropic elasticity in. Okay, here you have to put in to find to give its Young modulus and Poisson ratio as given in the questions. So the second part is on the geometries. So we have to check the surface body here, analysis type itself. You have to change to 2D. All right. So once you have done the modelings, okay, either you can use space claim or as well as dimension design modeler itself, right? So then you can go into mechanicals. So you can check your, I will say you can check your properties at here So you use change to stainless steels, okay? Then the property itself you can check the volume itself is around 2935.8 for the entire so-called bodies. So it's 2935.8. Then surface area is 978.61 around. So both I'm using design modeler and also space scale also giving the same results lah. So my advice, I mean, I go through some of your test project itself. I mean the question, I mean the solution itself that you have submitted. I think this is one of the part that you should also include in your reports lah. Here you have to tell me whether your model is correct. In the case of later on in your assessment, you need to model it. So next time, like for example, assignments, okay, so you should also put in one of the screenshot on these particular things, right? And also your mesh itself, okay? What is the size that you are using? What is the numbers, okay? Under statistics, you have these stat nodes and elements, okay? So that is where I can see the differences between yours and my results later on, right? So that is one part. The second thing that before I forgot is the project. ANSYS project found that you have saved and zip and you send to me. Okay, so I think you to be standardized, we should use zip lah. I mean the .ir, try to avoid it also. The other one is what, 7x, is it? We try to use .zip lah, zip lah. So just compress it. You can use the Windows compress versions to compress it. Okay, so that is the things that I need to highlight. Okay, when I go through your test. Okay, answer. Then come back to here. So here you can check back. I mean the thickness is already 3 mm. Material is stainless steel. The properties is there. Then that is things that you can look into. Then next will be the mesh, because this is just one component itself, so it doesn't involve any connections. So later on in 3-dimensionals, we have 3 components coming in. 3-dimensional model, we have 3 components coming in. Then there is connections coming out that you have to really look into it, whether it's connected correctly. The context, okay, is correctly assigned. So next is meshing. So here I'm using just quadrilateral dominance. Then sizing, I'm using 1.5 mm, right? So I use a local settings here when I call out, like I mentioned to you, inserts methods as well in insert sizing. All right. Then because it involves stress, so we use program control for element orders. So here is, of course, is quadratics elements, quadratics orders. So next we can go to settings. So if you come to here itself, right? So just now mesh, we have already seen this is the meshings. Then under the setting itself, then we have to set a fixed supports, okay, on these 6 edges, right? 1, 2, 3, 4, 5, 6. Then we have to set also a pressures 2 megapascal going down on this particular edge, the curvatures. Then after this, we can solve using finding the total deformations as well as the equivalent stress. Okay, so here the deformation is around 0.1314 mm. The stress is around 1.5 maximum at this particular so-called discontinuity here. Basically is when you have fixed at here. So basically here this region will induce a higher stress. So here is around 159.26. Okay. So if you can compare the U strength, then you can know whether it will fail or not. So we will move towards failure analysis. So once we know how to determine the deformations, I mean, solving the solid mechanics problems. I mean, here we're talking about the deformations. Okay, we get the U1, V1, U2, V2, U3, V3, all these informations from the stiffness matrix and determines, and the load metric determines we can solve the U. Then we can also post-process to get the stress, that what we have used to it, okay, in one dimensional, right? So from here, the stress itself, then next lectures, okay, we will go towards to see this value 159. What does it mean? 159, will it cause any failures in terms of statics, in terms of dynamics, okay, or in terms of statics? Static failure and static failures, okay, will it cause failure if you are inducing 159.26? So moving forwards, then we are looking into failure analysis. All right, so this is a two-dimensional analysis that we under 3Ds. Okay, I have another example problems of this. Okay, it's a base stand assembly. So you have a base here, you have a holder, then you have so-called pins. So here is made of structural steel, so no problems. Okay, you can use, you have a three components, a base, a pin, and a holder, three components. Then made of structural steel, so basically it's a default materials, so you do not need to create materials, okay? But you have to check whether the material properties, Young modulus and Poisson ratio is correctly inserted, 200 and 0.3. If no, then you can edit it. Then the boundary is the base itself is fixed. The surface 1, 2, 3, the three leg itself is fixed. Then you have a downward force 1 kilonewtons, okay, applied at the holder stop surface at this particular part itself, right? So we want to determine the deformations and the von Mises stress distributions, the equivalent stress and the total deformations of this assembly under the given loads and the boundaries. All right, so that is how I mean the problems that we want to analyze. So again, same. I mean, I have also shared with you the modeling under using design modelers as well as the space claim. You can try both. Okay, of course. Okay, you can also try using. You are familiar with other CAD software. You can also try to model it using your preferred CAD modeling software and imports, okay, from there. Okay, so but here is the 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 steps, okay, using space claim modeling tools and also the design model tools that you can use to model it. Okay, it's not a very complex model, so you can actually use this. Try using these modeling tools to model it. All right. So here I will want to say that you have a total of 3 components. So later on you will see that you have a total of 3 components. When you open the static I mean structure, the mechanical itself, you will see 3 components. So let me probably show you again. So you have 3 components, okay? So we have to make sure that, I mean, in the questions, I mean, the problem, you say that it is not fully bonded. So meaning by default, as I mentioned to you, component, if you have multiple components, right, it will by default, ANSYS will help you to bond them. So, okay, contact, under context, you have is bonded, meaning this particular holders as well as the pins as well as the base are all fully bonded. So fully bonded meaning no deformations, okay, and what we call no sliding as well, okay. So but here here it is assume is a no separation conditions for all contact regions. So whatever the contact between the holder and pins, base and pins, base and holder itself, we are saying that it's not bonded. It allows no, it is under no separation condition. Meaning that last week we have discussed no separation condition means is not deform. It cannot deforms. Okay, it cannot separate it from that two surface bonded two contact surfaces, but it allow slidings. Okay, so that is the no separation conditions means. Okay, so again is a static structures. So if you go through this, okay, under geometry, okay, so is the solid bodies, make sure it's checked. Then analysis is 3D. So by default it's 3D, so you have to ensure it. So if you are using space claim, then yeah, you can use both any the design model of space claim. So once you have done it, then of course you can go under this model. You will open mechanicals, okay, and see this mechanicals. So what I want to highlight to you is this particular parts. So under geometries, okay, so you can check under geometry. You have to make sure, I mean to check your properties. So I have the total volume of 29711, and because we have the density coming in of the materials, right? So we have the mass also is 0.23323. So I have checked, okay, based on the steps, the guides on design modeler as well as space claim, I can get a similar volumes and mass. So please also make sure you have that. Then the pin itself is structured steel. Remember to assign the correct, okay, correct so-called materials. So with properties, okay, the volume is 848.23. Then the holder itself, if you are talking about structural steel also, the volume is 3743. And finally, the base itself, under the properties, you have 25120. Right, so that is what I have for using space claim. So if you can, I can show you the one that I'm using, design modeler. So the under geometries, right? So under properties, so it's 29711.23323. Yeah. So holder also the same. You have 3743.2. The base is 25120. The pin is 848.23. All right, so because you have three components, right, and then here it will auto detect, okay, 1, 2, 3, right? So under previously you don't have under these connections here, you have the contacts, okay? So it will tell you the contacts of between the components, okay? Two components, the surface, when they are they are contacts, okay? Two faces are contacts. So basically it will by default it will be set as bonded. Okay, so you have to remember to change to no separation for all these three contacts, pin and holders. Okay, then pins and what we call the base, and also holder and the base. Okay, so remember to do that. Then here, the size I'm using 2.5 mm. Okay, the mesh here, that what I have is how it look like this. Then this is the nodes and elements that I have. Okay, you can check back later on. Then here, I have to make sure I fix the supports of these three faces. Okay, so at the bottom here, 1, 2, and 3. Okay, then also I have to insert a force of 1 kilonewtons. Okay, negative y on the surface, the top surface of the holders. Then we can find our deformations. It's around 0.007 mm, as well as equivalent stress is around 60 megapascal. All right. So you can try and see, okay, either using design modeler as well as design modeler or space claim. All right. So I will leave it to you. Any questions, you can come back to me.